me if my volume is low. Let us know and we can try to adjust the volume on Zoom. All right, let's get started. A little bit of a joke on the slide here. What's the joke here? Correlation. There's no correlation in this data. If you can see constellations better than you can see the line, then you probably shouldn't be fitting lines. That's a little funny. All right, so lecture 31 is least squares. So today, I always say it's fun, but today we get to do visualization, optimization, lots of three-dimensional plots, so lots of fun stuff to look through, and have a bunch of exercises we'll actually walk through as discussion. So it should be a pretty fun interactive lecture for the few of you who've made it in the rain. All right, so announcements. Project 2 checkpoint is due today at 11 p.m. Full project is due 4/14, so next Friday. Early submission bonus again for 4/13 for next Thursday. Homework 10 is out and due 4/12. And a quick reminder again, we have a guest lecturer on Monday. This is DJ Patel. He was the chief data scientist for the Obama administration. He's done a lot for the US government. He's a pretty famous figure in data science. So I would recommend attending lecture and ideally attending early. You all know this because you're attending lecture today. If you can get in early, you'll have hopefully your favorite seat. I expect it hopefully will be pretty well attended on Monday. It's also in Wheeler. I mentioned in the beginning of this class, we would probably have the speaker. I was hoping to book a bigger lecture hall, but Wheeler is all we could get. So, all right, so moving on. So Monday, we talked about how to measure the relationship between our data. We introduced the correlation coefficient. Wednesday, we started to do prediction. We derived the linear equation that we use to make predictions. Today, we're going to go into what it means to be a best linear predictor. Linear regression, quick recap. So our goal is predict a y value given an x value. And here, I didn't say this earlier, but it's very important that the x and the y, these should be numerical values. These are not categorical data. We will actually cover in a few days how to deal with categorical predictions. In this class, we won't spend much time thinking about how to use categorical features, categorical x values, but that's something that's pretty widely studied. And when you take later classes, you'll see more about that. All right. Some examples. So things like predicting number of hospital beds available using air pollution. Kind of interesting. So if I knew the amount of air pollution, how many people are going to be in the hospitals. It'd be good if I were forecasting a big fires, taking off. Am I going to have enough hospital beds next week? Predicting house prices given house size. Once upon a time, I had a company that actually helped companies like Zillow do predictions. And this is, they have these scores for what the price of your house should be or what it's estimated to be based on the houses around it, the house size and other things. So it's a pretty common use case for prediction. Or predict number of app users using just the number of downloads. If we had some data about relationship between app users and downloads, we might be able to use number of downloads to make predictions about how many people are actually using our app. So examples of prediction. These are all regression. Regression, critically, I'm predicting a numerical values, and it's something that's continuous. We will, again, in future lectures, talk about what if I want to predict, is this spam or not spam, or is this photo safe for work or not safe for work, right? These are more binary classification decisions. So that's called classification. We'll get to that. Regression estimate. This is the equation that we derived. So predict y using x, find the regression estimate of y. Here's how we do it. So convert the given x to standard units. Why is that circle? Okay, there you go. So the process for doing this, which is what you would do on an exam, as you given an x, you're going to convert it to standard units, multiply by r. And then what that gives you is the regression estimate for y in standard units. And we need to convert it back to the values of y, right? So last lecture, I had an example like this. I've modified this example. I'm going to run this again. It's a different setup. Let's take 1 minute. This time through, can you tell me what the number will be? So here's a setup. I have a midterm where we got 70, average of 70, standard deviation of 10. I have a harder final. Again, we're not shooting for that, but let's say we had a harder final. The average is 50 now. Standard deviation is 12. If the correlation is still 0.75, and the student got a 62 on the final, and I'm using linear regression to predict what they would have gotten on the midterm, to clobber their midterm score. Let's say they didn't take the midterm. What would I predict? What would their score be? All right, Let's take a minute and do this. Talk to people. I want a number. I'm going to pick someone at random, and you're going to tell me the number. So you should have a number in mind. What do you do? Does anyone have a number? Raise your hand if you got a number. All right, a little more time. Come on, people get the numbers. You can do this one. Who's got the number for standard units of X? Who's got that? At least one of you has it, right? What's the number? 1. Okay, how do I do that? So standard units of X. My X here is the final, not the midterm. So I'm going to take X is 62. That's what we got. Subtract the mean on the midterm, or sorry, the mean on the final, 50. Divide by the standard deviation on the final. That was 12. 60 minus 50 is 12. 12 over 12 is 1. Okay, good. Can someone tell me what the Y value is in standard units? Who can tell me what the Y value is in standard units? More people should raise their hand. Okay, I have to take 1 and multiply it by R. What is the Y value in standard units? Thank you. Okay, it's 0.75. I made these numbers easy. So 0.75, that's R, times Y, 1, 0.75. What does that mean? How does this student do on the midterm that they didn't take? Above average? Yeah. How much above average? 0.75 standard deviations above average. So I just told you that. You should be like, okay, the student got 0.75 above average. I know average was 70. And then 0.75 of 10, that's 10, 1 standard deviation is 10. What's the score on the final? Who's got the number? Someone yell out some numbers. 77.5. How did you do that? So I have 0.75 times the mean, sorry, times the standard deviation. So that's how far away from the mean the student did. So they were 0.75, so that's 7.5 above the mean, and the mean was 70, so they got 77.5. Does this make sense? Raise your hand if this makes sense. All right, we're starting to get there. It's tricky, it's important. Now, here's the real question. Does this clobbering policy help or hurt you? So who benefits from a clobber? Who gets harmed by a clobber using this calculus? Quick discussion. For those of you who are clobbering, think it through. Is this going to hurt or help? All right. If you got a high score on the final, is this policy going to be a good thing for you or a bad thing for you? Good thing. Well, you got a high score in the final, so that's pretty good anyways, right? Is it good though? Not good. So you did well in the final. We have this regression to the mean thing going on here, right? We took 0.75 of your deviation on the final. You did, what were you? You were 1 standard deviation above the average on the final. But the correlation coefficient is a number less than 1. So you did worse on the midterm. Right? Flip it around. So you didn't do so well in the final. It's going to help or hurt? Help. Why is it going to help? Regression. Why is it going to help? It's going to pull you back up. Yep. So you got a number less than 1 or less than the mean. This is going to bring you closer to the mean. Your standard deviations from the mean are going to get smaller, right? So it's going to raise your score. Should we use this approach to clobbering? It's actually a pretty fair approach for clobbering. There are other ways we can clobber, and I actually don't know what we're going to end up using in the end, but it's actually pretty reasonable if the grades have a strong correlation and sort of subtle if the distributions are more Gaussian for grades. Okay. All right, so this is called regression towards the mean. In last lecture, we then worked through the calculation of the slope and the intercept in the original units by doing some algebra to transform that equation of r times standard units of x equals the predicted y in standard units. All this should be good. Given that information, what are the units of each of these quantities? All right, so let's use an example. So we're trying to predict candy prices in dollars, so that's our y value, given the sugar content in grams, that's our x value. What is the units of r? Dollars per gram, grams per dollar, nothing. Who says dollars per gram? Grams per dollar? Nothing. Nothing. That's correct. Remember, r is a number between -1 and 1. It is unitless because it is a product of things in standard units, which are also unitless. Okay, how about the slope? What's the slope? Here's the slope. What's the slope? Y values in dollars, x values in grams. Slope is in grams per dollar. Dollars per gram. Unitless. Okay, so r is unitless, but y is in dollars, x is in grams. So I have unitless thing times dollars per gram. So it's in dollars per gram. Good. How about the intercept? My regression equation. What's the intercept? Someone shout it out. Dollars. Why is it in dollars? The average of y is in dollars. Slope is in dollars per gram. The average of x is in grams. Grams over dollars per grams. The grams cancel out. So we have dollars and dollars. Everything's in dollars. Okay. These are actually interpretable. So I tell you the intercept is 20. That means that that's crazy. You charge $20 for candy that has 0 grams of sugar. She might be reasonable. These are diet candy. Maybe they're expensive. Okay. Got it? So units, put them in here for study purposes. So r is unitless, slope is in dollars per gram, and the intercept is in dollars. All right, time for some demos. Today is fun. Okay, so I have standard units. These are code that we've had in all the previous lectures for the past few weeks. Standard units, again, take my value, subtract off the mean, divide by standard deviation. Correlation is the product of the standard units of two variables. So of x and y, I take standard units, take the product, and I take the mean of that. Okay. Slope and intercept, I just implement these equations. So I need the correlation r, I need the x and y standard deviations. So I have x and y standard deviations, and then r, the slope is r times y standard deviations divided by the x standard deviations. I'm not going to bore you with the intercept. It's the same thing. I take this equation here, and I implement it down here. Got it? And now, to make a prediction, if I have the slope and I have the intercept, the predicted value for my y is the slope times the x value, the observed x value, plus the intercept. Simple equation of a line. Quick pause, questions at this point. We do making lots of plots and three-dimensional pictures and spinning stuff around and so on. Questions on Zoom? How's Zoom doing? Zoom's good. That's weird. All right, let's make some predictions. Some new data for today. This is the 2016 demographics for the US districts, for congressional districts. What we have here is the state, the district, the median income, the percent voting for Clinton, we'll ignore that for today, and the percent of college-educated people. And I think today we're going to figure out if college education improves your income. Let's figure it out. Here's our scatter plot. What do we see here? X-axis, percent college educated. Y-axis is the median income. Is this a linear regression candidate? Does it look linear? What's the relationship? What's the slope? I don't know. What is the R value for this? I want to wager a guess. 0.3? No? We'll go up. Is there a 0.5? 0.6? 0.7? Wow, 0.8? 0.9? 1.2? No, okay, good. So it has to be number between -1 and 1. It's positive. We know it's positive because it's going up and to the right. It's positive. And it's pretty correlated. Let's see what it is. 0.81. Wow, you all were very close. I don't know how you did that. I would have guessed like 0.6. I'm bad at guessing these things. Okay. I probably committed a sin. What did I just do? What did I do wrong here? Maybe I didn't do anything wrong, so I didn't say something wrong, but what could I be doing wrong here? I just computed correlation between two variables. Thoughts? What did I do wrong? Bingo. Okay, so I just showed there's a correlation between these congressional districts, not states, but pretty close. These congressional districts, the correlation between the percent of college-educated people and the median income, right? And that's the average, that is the proportion of college-educated people. So that is an aggregate statistic. So this is an ecological correlation. It's totally reasonable. The way to think about this would be to say, well, district, if we think there's a relationship here, a district that has more college-educated people would suggest that that district is going to have a higher income. Is it causal? No, we don't know. We need a randomized control, but there suggests a relationship at the district level, but it doesn't. I can't take this data and go, well, there's a relationship between college education and income for an individual, right? There might be, but this data is aggregated. I highly doubt it's 0.81. If I were to blow each of these points up into the people, there's people who make a fortune. They took the median here. There's going to be people off the charts that have no education, lots of education. Each one of these dots is going to explode into a cloud, right? And this correlation will become much, much smaller. Kind of look at this data. I like this tool because I can like click in. So there's California. What's another one to look at? What's in the news? Tennessee's in the news, right? Where's Tennessee? Yeah, so you get different states had different levels of correlation between these different distributions of income. So if we actually do this analysis at individual state level, might see very different effects, right? All right, so computed correlation. Let's make some predictions. So I'm going to compute the slope. How does it work? My function takes a table and the column names, so college and median income. That's going to be the slope. This is going to be the intercept. Intercept, so you can all see it. Let's run it. All right, so what's slope here? Slope is in what units? Dollars per percent college educated. So every percent increase for your district gives you $1,000-ish increase in median income. It's pretty good. The intercept is saying what? No education equals 20,000 median income, 20,000.8. 20, I guess $20,802. Okay, that makes sense. Let's actually plot this. So first thing I'm going to do here is I'm going to use my prediction function, and I'm going to predict for my demographics. This is going to be my X value. Sorry, my X value is college percentage. Why does my predict linear take the median income as the argument here? It doesn't need to. That's a bug. Why does it need it? Oh, it doesn't. It does need it. Sorry. My predict linear actually is going to compute the slope and the intercept on the fly. So let's go back here for a second. All right. Predict linear, my function I wrote earlier, is going to make a linear prediction. It needs both the X and the Y columns in my data because inside this function, it's going to recompute the slope and the intercept. And then for each of the X values for which I already have the Y value, it's going to go ahead and make a prediction anyways. Okay. It's a little weird. So I'm making predictions for the things I already have. So I have the actual median income, and then I predict the median income. Why might I do that? Why would I make predictions for things I already have? Yeah, it's a good reason. So I have data. I want to see if my prediction's any good. And we're going to spend the second half of this lecture visualizing what that really means. Another reason I might do this, if I really do believe my model, is I want to know what data disagreed with my predictions. Those might be data worth looking at, right? If I believe, and this is a pretty good correlation, the things that are really far from my predictions might be concerning. Maybe the data is wrong. So here's my plot. Each of these yellow dots corresponds to the prediction that I predicted for this dot, right? My predictions. Let's do one thing. I want to actually make predictions between the dots right here. So, if I had this, whatever this number is, 68, 69% college educated, what would be the prediction? So here, what I'm going to do is I'm going to take a range from 0 to 75, and I'm going to compute my y value is going to be the slope number I computed times that vector from 0 to 75, just the array, plus the intercept. And that's going to give me a nice red line that goes through everything. This is the line you'd see in Excel if you said fit a linear line to my data. So it makes predictions between the points. It's got something pretty close to here, so I kind of guess what these two values are, the difference. So that is my linear fit. Good. All right, so is this fit a good fit? Is this the best fit? And this comes back to this earlier picture here. Could I have done better? How could I have moved this line? In order to answer these kinds of questions, I need a good measure of the error in my model, my linear equation. To answer that, I have to return to my slides. So we did least squares. Now let's talk about error. So we're going to use a very simple notion of error for this model. So we have what we actually observed, the median income for the district, and then we have our estimate. And we're going to say the error is the difference. It's a pretty simple notion of error. Some errors are going to be positive. What does a positive error imply? Did I underestimate or overestimate? Under, right? So the actual value is big, my estimate's small, the actual minus estimate's a positive number. Negative errors, like these guys here, I overestimated, right? So my error goes down, points downward. Okay. So positive and negative, hopefully small, that's the goal. So I want to measure the rough size of the errors overall. How would I do that? I got an error for each data point. What should I do? Take the average. We'll see why that's a problem. I'm going to actually take the square. And this is a recurring theme in this class. We've been taking these numbers. When I average them, we'll see in a moment, they're going to average to 0. That's annoying. So I'm going to square it so they're all positive numbers, and then I'll take the average of that, right? So take the mean of the squared errors, and I'm going to take the square root. Why would I take the mean of the squared errors and then take the square root? This is a recurring theme again. Why did I take the square root? For fun? Why? Units, right? So my errors are in what units? If I'm measuring dollars, my y-axis is dollars. What's the error in? Dollars, right? It's a difference in my predicted dollars and the actual dollars, right? If I take the sum of the square of the errors, or the mean of the square of the errors, that's in square dollars. That's hard to reason about. So my average error is in square dollars. If I take the square root of it, I'm back in dollars. And that's something we can reason about. So better units. And this is called the root mean squared error, or square error, RMSE. I think slides are boring. All right, so I have my y value is my median income that I actually observed. That's what I observed in my data. My prediction, I use this predict linear function again. My error is my y value minus my predicted, so y minus y predicted. And I'll put this in my table here. So now I have my prediction and I have my error. Okay. So as I said earlier, one of the things you might want to do when you make these predictions, and if you do believe, and I kind of believe this is a good fit, what are the things here that look weird in this data set given this, right? This point here is weird. And maybe this point here is kind of far from it. This point is pretty far. What's going on, right? So the things that have high error in both directions might be interesting data. And so I might fit this model just to figure out what things don't agree with my model. Let's see, what doesn't agree? So how am I doing that? So I'm going to take the absolute value for simplicity of the error. We'll come back to square in a moment, but I'm just take the absolute value, simple units, and then I'm going to sort by the things with the largest absolute error. What do I get? Any guesses to what I'm seeing? New York. I'm going to guess it's New York City. It just has a very high median. Actually, that's not very high. Huh. It's a high error. Maryland, median income. Let's take a look at these. So this is District 2, District 5, District 15. So these have large errors. So my model didn't estimate the value correctly. You got California in here. So these are the higher incomes, yeah. Let's look at it. So what does this suggest? Let's visualize the errors. All right, so what I've plotted here is the actual gap. So this is the error. That's the number that I'm computing. And then here are the points that have hires, or the large errors, right? So this is District 18. Is this up in this chart here? District 18 is up here. It's a pretty big error. District 10, maybe so these are high income districts. These could be like the capital. This might be New York City, or this might be Los Angeles. These would be the data points that I'd want to explore deeper using this model. So just looking at errors already, that gives me some a tool to try to explore what's an outlier in my data. What are weird points? But that's not the goal of this lecture. The goal of this lecture is to actually use this error to build a better model, or to find the very best model we can for our data. Let's do that. All right. Oh, I guess one more thing to look at. So these errors should hopefully be centered around 0. That's kind of the idea. There'll be some negative errors, some positive errors, have some spread. This is the spread in my errors. This error, by the way, is also called a residual, and we're going to spend a whole other lecture looking at how to diagnose these residuals, what they tell us about our data. All right, so what is the average of the errors? Kind of gave it away. So a neat property of these models is that the average of the errors is 0. This is a computer scientist version of 0. That's a very, very small floating point number. Okay. So the average of the errors is 0. I could take the absolute value of the errors and take the average of that. That's reasonable. That is actually a thing that's called the mean absolute error. That's a number. That's in units of dollars. Okay. There's another error, which is the error that most people would use when doing this kind of analysis, which is the squared error. So this is the mean squared error, and this is in units of dollars squared. So that's I don't know what that number means. I don't know how to think about that number. But if I take the square root of it, that's in dollars again. Okay. Now, why is this number bigger than this number? That's weird. So when I take the square of the errors, I'm going to be really sensitive to these faraway points. And they're going to have a big effect, and they're going to bias my error towards those points. So the squared error is going to be sensitive to large number, or to large deviations from the line. And that's going to be important to think through as we apply these techniques. Both of these error functions are reasonable. In most of statistics, we'll use this one because it's mathematically easier to do equations and analysis with. But with computers, this error is also perfectly reasonable, and people use this as well when they're worried about extreme outliers when trying to fit their data. Yeah. So the root mean squared error, an example is basically always, because mean squared error, any tool that does regression will typically use that form of error. This has interesting connections. Even the mean itself is defined in terms of this error. So the mean squared error is it's a super common error. It is also very easy for computers to optimize. It's also easy for you to use calculus to solve for the best equation with mean squared error, or with root mean squared error. Either works. With absolute error, you have to use computers. There's no magic calculus, no way to solve this problem. You have to do numerical optimization. Good news is, in this class, we're not going to teach you calculus. We're going to teach you numerical optimization. We'll do that now. So we'll be able to use both of these. So we already did this discussion question. All right, so how do I use air? I'm going to make a new function called demographics RMSE. This is a function that's going to take a slope and an intercept and return an error. So what's that doing? So inside that function, I'm going to take the slope, the intercept. I'm going to say that's the line you wanted. Great, I'll make a prediction. I'll get the actual value. I'll take the predicted minus actual, and I'm going to return the square root of the mean of the errors squared. It's a pretty straightforward function. It computes the root mean squared error. What does this function look like? All right, so I can plug in my demo slope and my demo intercept, and that had $9,398 as the root mean squared error. What does this look like? All right, let's try another way to visualize it. So by the way, this visualization code, you can ignore everything that involves Plotly, unless you want to learn more stuff, and then you should read about that. But we will not be asking this stuff on the exam. Okay, so here's my original line, $9,398. Here's if I decide, let's make the slope 1,000 bigger, make the intercept 50,000 smaller. Here's another line. All these errors, lots of errors. So each invocation of this function, of this RMSE function I built with a slope and intercept, will give me a different line and a different error value. Kind of see where I'm going here? I've got a function that I want to make as small as possible. I want the least error that I can get on my data. How do I do that? All right, let's try to vary something. So here I'm going to try different versions of the slope. I'll take the slope we've been using for the past few lectures, and I'll go, minus 20 to 20 off of that. And I'm going to plot, I'm going to compute the RMSEs. I'm going to plot the error for all these variations of my slope. What's this going to look like? Any guesses? Hold your hands up in a shape that you think this looks like. Is it like a line? You can go like this, no? Come on, give me a shape. Yeah, it's like this, right? Let's see. Zoop. All right, so here's the slope we picked. Here are other slopes we could have picked. If we kept the intercept the same, makes this little bowl. It's a parabola. Kind of makes sense. We're doing squared stuff, so it's going to be a quadratic equation, so it's going to be a parabola. Okay, well, that's a pretty good slope. Let's see. Can we change the intercept, make it better? So we'll take the intercept. I'll go minus 2,000, 2,000, steps of 100. Let's make another plot. Here's the various intercept values we could have picked. We hold the slope constant. And again, the intercept we chose seems to be the best. So what do we think here? Do we have the best line? It has the best slope if I hold the intercept still. It has the best intercept if I hold the slope still. We haven't actually shown that this is the best, and maybe if I move both of them at once, it could be better. It turns out this is the best, and this whole surface is a giant cup, and I'll show that in 3D in a moment. But looking at slices of this, it does appear to be pretty good. All right, so let's change the slope and the intercept at the same time. Let's take a little bit more work here. What's this going to look like? I'm going to make a surface from above. So each point on this picture corresponds to a choice of slope and intercept. It corresponds to a line fit through this data. And the color here corresponds to the error, right? This little red dot here, this is the slope and intercept we've been deriving the past few lectures. It is at the lowest point, the darkest point in this plot, at the lowest error, right? And this whole thing looks like a bowl. And because we can do it, we will. This is actually what it looks like. So we have a three-dimensional surface. For different slopes, different intercepts, we have an error. And this little red ball at the bottom of this thing, trust me, there's a little curvature here. There's a very, very small amount of curvature here. This is really at the bottom of this bowl. Got it? So what we've been doing all along is trying to find a line that's at the bottom of some error surface. And we got to pick that error surface. I chose the RMSE here. I could choose absolute error. I could choose any different error function I wanted. My goal is to find the point at the bottom of this error surface. And that point is a line in my original space. It corresponds to a slope and an intercept. Right? I've talked a lot. Are there questions at this point? no questions. And Zoom, no questions. Either making no sense or a lot of sense. I'm going to go with a lot of sense because I want to keep going. Okay. All right. So we showed what the errors look like. Now I'm going to show you an amazing tool. This is numerical optimization. It is an approximation method, but incredibly effective. All of machine learning today, I'm going to say all of the machine learning you use, the fancy stuff, ChatGPT, when you talk to your phone and it talks back, all of that is prediction. All of that is using these techniques that I'm about to show you, numerical optimization. So it's a really powerful tool. There's slight variations that we use that take information from calculus to guide us. In this lecture, we're going to use something that doesn't even touch calculus, but still very effective. Our goal is to take something like an error function over a choice of models. So my slope and intercept, that gives me a line. We're going to call that a model. I want to minimize the error. I'm going to apply these numerical methods to minimize that. So here's how you do it. You say minimize and then your function. We're done. That's it. Okay. And it's going to return an array corresponding to the best arguments, the best values of that function. So this is really arg minimize, find the arguments that minimize the function you passed in. How does it do it? Magic. I'm not going to teach that in this class. If you want to know how it does it, take an optimization class. That won't actually cover how it does it either. This uses Powell's algorithm. I don't think we teach that in any of our classes. So this is a technique that doesn't even care about the shape of the surface. It's going to just keep probing and try to find the minimum. Pretty powerful. All right, let's try it. Okay, so first, before we do some error minimization, let's minimize a parabola. Here's our parabola. Here's the equation I chose, x minus 2 squared plus 3. What is the minimum of this equation? Right here, x equals 2. We knew that because, when x equals 2 here, this is 0. That's the smallest this can be. Okay, now let's ask computer, who doesn't get to see the algebraic form of this equation. It just gets f. We can call f a bunch of times. It's calling the SciPy minimize function. Boom. That's a computer scientist version of 2. Close enough. Great. So this magic function minimize just takes your function, minimizes it for you. So we can minimize function. This gives us the value that minimizes. Again, it's really argmin, so it gives me the x value. X min is 2. The value of the function at 2 is what? F of minimize of f gives me the function value. That's 3. That's this point right here. 2, 3. Cool. So now know how to use minimize. That is our point. Good job, us. Just to show you how crazy this thing is, for those who's taken an optimization class? Good. Okay. Well, if you've taken an optimization class, this is hard to optimize. It's got all these bumps. All your mathematical techniques kind of get stuck in these bumps. It's a lot of work. Let's see how this function performs on this, right? So I've created a complicated function. This is the equation of my complicated function. Here's the code for my complicated function. That's the line. Let's minimize it. Did I get it right? So that looks like the minimum, 0.74 is my x min. And yeah, it looks like I got it right. Puts the red dot right in the right spot. It's kind of magic, right? Yeah, it's magic to me too. Again, because we can. Why stop at one variable when you can have 2, right? So here's a function. This is a crazy function. Any guess what this looks like? Not at all, right? Me neither. So let's plot it. So here's my function. It takes 2 arguments, a and b. It does math. It has a minimum. Cool. What is that the minimum of? Let's see it. Here's our function. Zoop. And there it is. Found the minimum. Magic, right? You should take an optimization class. Stuff is super cool, but I'm not teaching it today. So it works. It works for crazy stuff. Let's see if it works for our stuff. So demographic RMSE is a function I had earlier. I was just plotting it. I say minimize. What does that give me? 2 numbers. This number is the slope, remember, and this number is the intercept. That's the first and second arguments of this function. Oh, did I mess this up? I did. No, I didn't. Here we go. Sorry. So here's my demo slope and intercept. This is demographic slope and intercept we've been using throughout this class. And the thing that minimized the RMSE using magic gives us basically the same result, right? So using numerical optimization, the thing we've been using all along does in fact appear to minimize this root mean squared error. If I change it to mean squared error, get rid of that square root. Try it again, what's going to happen? Be the same thing or different? The minimum of the thing, when I take the square root, doesn't change the minimum. It just changes the value of the minimum. It doesn't change the argument. So we get the same value. In fact, I get something a little bit closer. And this is getting back to the mathematical properties. So squared functions are easier for us to minimize. They're kind of smoother. So the computer likes that one better. And it gets, again, very close to what we had derived by inspection in previous lectures. So I said we can change our error. Why not? So let's use the mean absolute error. So instead of taking the mean of the square, I'm going to take the mean of the absolute error. What does that look like? That's another function. Minimize it. Magic. I get more numbers. I get my new slope and my new intercept. Are they the same? No. So I change my error function. Different choice of error function, different equation, right? So all along we've been talking about an equation of a line, but that's really the equation of the line that minimizes the mean squared error. We could have chosen to minimize the mean absolute error. There isn't an equation for that line, so I couldn't have shown it to you, and we can't ask you it on the exam. You have to use numeric minimization to solve this problem. Is it different? How is it going to be different? Let's look. Zoom in a little bit here. Which one of these is the mean squared error of these lines, and which one of these things you think is the mean absolute error? I don't actually know myself. All right, so least square is up here. The mean absolute error is here. Go back out again. So I'm going to say the least squares is getting pulled by these points. It's very sensitive to these outliers. And so if I have an extreme point, which if I had more time, I would move one of these points way up here, I can cause this mean squared error, this blue line, to start following that point. But the mean absolute error is not going to follow that point. We're not going to follow it as closely. So it's more robust. Good. Return to slides. Okay, cool. We have just enough time to do some really cool visualizations. All right, so least squares line, the line we've been using all along, turns out, minimizes the root mean squared error, the RMSE among all lines. It also minimizes the mean squared error, so equivalent to minimizing the mean squared error. It has names. These are the names you would hear in a textbook or in a software package. The line of best fit. That's a lie, actually, because there are many lines of best fit, depending on your error function, but most people in the world, when they say best fit, they're referring, in regression, they're referring to the thing that minimizes the mean squared error. The least squares line makes sense why. It's the thing that has the least squared error, or sometimes just the regression line. Any questions at this point? I've been going a little fast. Pause for a second. Zoom's going okay? Weird. Fine. This is the fun part. Okay, so we've been fitting a line to some data. In the real world, you get lots of X values. You get lots of features about a person. Maybe I can use to predict your final, your midterm score, I can use not just your final score, but all the scores throughout the class. What if I use all of them? Maybe that's a better way to predict something about you, right? So I said in earlier lectures, I wouldn't teach you this, and I changed my mind last night. I will teach you this because it doesn't change anything. So you already know how to do it. We're going to go ahead and actually do multiple linear regression, and we're also going to fit nonlinear curvy surfaces in 5 minutes. Let's do it. All right, to illustrate this, I'm going to bring back in our cars data set. I'm going to make it 3D because it's three-dimensional data, actually. So we have the acceleration in miles per gallon of various vehicles, right? And I'm going to say, what would be the predicted price for that vehicle for different accelerations in miles per gallon? So what do I want to do here is I have all these points. I'm going to start with the linear equation. What's the linear equation look like in this three-dimensional space? What am I going to do? A line could work, but actually I want a plane. I want to, for any acceleration in any MPG, I want you to tell me what the MSRP, that's the manufacturer suggested retail price, or just for simplicity, the price of the car. Okay. So I need an equation. And here's my equation. I'm going to say the price is going to be some slope times the, oops, sorry. times the acceleration plus another slope times the miles per gallon plus some intercept. That's my model. Okay. And I want a good model, so I'm going to minimize the error for A, B, and C. How do I do that? I take the actual price, I take the acceleration, miles per gallon, and my prediction is A times acceleration plus B times miles per gallon plus C, my intercept. And then my error is going to be that says mean squared error. Let's get rid of the square root. I don't want a square root here. Oh, actually, I called this RMSE, so let's make this RMSE. Okay. So this is hybrid RMSE. So I'm taking the square root of the mean of the actual minus predicted. I haven't done anything different. The only thing I've changed here is I've added an extra variable, miles per gallon, and I gave it an extra slope, right? Same as we were doing before. Magic. I got 3 numbers back. I just fit my model. What do those numbers mean? I have no idea. Let's take a look. I have an error. This error is in dollars because it's root mean squared error. So that's $14,000 is the root mean squared error. It's a lot of error. It's pretty expensive, the deviation. What does this look like? All right, to figure out what this looks like, I'm going to look at a range of values for the MPG, a range of accelerations. I'm going to make lots of predictions on a grid. I'm going to make a grid of predictions. Let me just show you what this grid looks like, and we'll talk about it some more. All right, so that's my model. That's the grid. So basically, for lots of values of acceleration and MPG, I looked up what the model predicts, and that's a point on this plane. And I just said, plot all those points on a plane. That's my model. Do we like this model? Not bad. Feels like it's kind of close to the points. Could we do better? Certainly. This data is pretty curvy. I feel like there's like let's go back up here. From this angle, I feel like there's some curvature here. Maybe there's some curvature here. Let's make the equation, the model, more complicated because we can. So why not? My prediction is going to be A times acceleration plus B times miles per gallon, same as before. Let's go ahead and take the acceleration squared, miles per gallon squared, fit a more complex function, right? Magic, I say minimize my function. It returns the minimization of all these variables. Okay, is this any good? Well, what's the error? 13,000. What was it before? 14,000. So we're doing something. We made it better. What does it look like? Well, I'm going to have to probe my function across all these different values. And now I have this. Did this improve my fit? At least it reduced my error. Would you use this to make predictions? I don't know. Would you? So what did I do here? I started with some data. I could have just started with miles per gallon to predict price, and that might have been a good place to start. And I said, well, you know what? I have acceleration. I should use both those things. And I just made my model a little bigger, added an extra feature, an extra column. And I used this to make a prediction. And I got a prediction. It was a plane. If I had added more features, could I have plotted it? No. So if I started adding, weight, it would be hard to plot my miles per gallon acceleration and weight against the price. That's a 4-dimensional plot. All right, so I added more features. I got a plane. That was the thing that minimized my squared error. I could have said, maybe I should use absolute error because they're outliers. And I might, that might have been a better way to approach this problem. There's some of these extreme cars like this nonsense Lexus that's, terrible, good acceleration, bad MPG. Yeah. Could have changed my error. That might have been a better way to get a good fit to my data. But I said, maybe there's more nonlinear structure. And because I have these tools, I can go ahead and change my model and make it more complicated. I can add squares of terms. I can add whatever shape I think would better fit my data. And I can measure the error. There's a huge flaw in what we just did. We won't spend a lot of time on this flaw. But as I make this model more complicated, I have a tendency to maybe try to explain the noise in my data too. The errors will get small, but it may not be a good thing. So in future lectures, next week, we'll start to talk about the residual plots and how we understand how good this fit is, and whether or not we should do these kinds of manipulations. Okay, that's it. Monday, guest lecture.